I was just finishing medical school when we were suddenly confronted with a new medical mystery. Deadly new disease. We had no idea what caused it. We had no treatment for it. And essentially, we were left to watch as it killed hundreds and then thousands and then millions of people. Obviously, this was AIDS as the disease and HIV, the virus, as the cause of it. And even today, with treatment available, it has to be given lifelong or the virus comes surging back. And 40 years into this, we still don't have an effective vaccine or a cure. But then there was another medical mystery that occurred as we were going along. It turned out that certain people living with HIV, were able to survive for decades without any treatment, remaining entirely well and thriving. So how is that possible? Well, the answer to those mysteries was actually found in the human immune system. And it points to the path forward, which is basically, I believe, learning from patients and then programming the immune system to replicate what happens in those successful patients to ultimately program the immune system to attack deadly pathogens before they have a chance to do significant damage, like you'd program a computer. So the story I'd like to tell you today is how we learned from patients and how we went from really baffled and powerless in the beginning of the epidemic to excited and enthusiastic now about the prospects of programming an immune system with implications, I think, that are far beyond HIV. The first AIDS patient I saw was before the disease even had a name. I had just graduated from medical school. I was working at Mass General late one night on call in the emergency room when a patient came in, a 19-year-old, with multiple infections and multiple cancers all at the same time. We were shocked. Even the senior doctors had never seen anything like it. And they told us we'd probably never see it again. Unfortunately, the patient soon died. But then another patient just like that came in, and then another and another. And it became very clear that this was a new disease and that we were powerless to treat it. It took a few years before the viral cause of this disease, HIV, was identified, and before we understood why it was doing such a bad job, why it was so lethal. And the reason for that is that it actually infects a cell of the immune system, and that actually should be helping to protect against infection, a cell called the T helper cell. So viruses are essentially packages of genetic material. They can't replicate on their own. They have to infect cells to do that and force cells to become factories making more viruses. And the cell that HIV infects is this T helper cell. So the question is, normally the body would fight back against an infected cell, but that wasn't happening in these HIV-infected patients. So the question was why? And I decided that I would try and help answer that question by focusing on patients that we were following in the clinic and trying to understand what their immune systems were doing to help fight back. And so I did what scientists do. I wrote a grant, and the grant was rejected. And the reason it was rejected was that the reviewers felt that, of course, killer T cells couldn't exist in this situation. That's why we had AIDS and why people were dying. But fortunately, we had a second chance because of philanthropy. And we went on to actually discover that not only were killer T cells present, they were present in huge numbers. It's just that they weren't doing their job. And that really started us on a long path to try and understand why that was. So a real turning point for us came about 10 years later, when treatment was still not available. Our clinic was really a heartbreaking place. It was filled with people with advanced stages of AIDS, all young, and that particular day, there was one patient there that stood out because he looked entirely healthy. And he was the one who came forward when I called out the name for the next patient I was supposed to see. In the exam room, he said that he had hemophilia, that he had been infected with HIV 17 years earlier, and because of contaminated blood products. But in fact, he was entirely well. He'd never taken any anti-HIV drugs. He didn't have that special co-receptor that modulates HIV infection. And he wanted to know when he was going to die and why he hadn't died already. So I, in my wisdom, thought, this person can't possibly be infected. Nobody lives this long. I retested him, and in fact, he was clearly infected. More astonishingly, I measured the amount of virus in his blood, and it was so low that it was barely detectable. So as these results came back, a chill went down my spine. I thought, oh my God, this person may be controlling the virus with his own immune system, something we thought wasn't possible. Maybe not everybody dies. And so I drew his blood, went back to the lab, and discovered that he had the strongest killer T-cell responses we'd ever seen. And moreover, he had normal numbers of helper T-cells in his body, indicating that they were being protected somehow since the virus was clearly in his body. So to us at that point, it seemed HIV is revealing a secret, and we have to pounce on this. So I did what scientists do. I wrote a grant application, and the grant was rejected. And this time it was because the review committee felt that it was just a little too risky to fund. It was too early. We didn't have definitive evidence that these killer cells were really what was protecting things, and we only had one patient. But fortunately, philanthropy came through again with funding from the Mark and Lisa Schwartz Foundation. We were able to put together a cohort of about 1,000 of these people that control spontaneously without medications. Turns out it's about 1 in 300 people who become infected. Rare, definitely, but definitely real. And from those individuals, we were able to show that, in fact, the killer T cells were key to control, but we just didn't know how are they working in some people and not working in others. And so the question was, how do we get HIV to reveal more secrets? At that time, we were working on another cohort of outliers, babies born with HIV infection because of mother-to-child transmission. And babies do very badly when they become infected. So the question was why, and could we get a clue from studying them as to what was missing that prevented them from controlling? So to do those studies, we established collaborations in South Africa, which had a heavy burden of mother-to-child transmission. And with our collaborators there, we established a small laboratory, immunology laboratory, and then found that what was happening was in the mother, the pregnant mother, the virus was already learning how to evade her killer T-cell response, so that when it was transmitted to the baby, it already had a head start in evading the baby's immune responses. Another secret revealed, how could we do more? And we certainly felt that more needed to be done. We were able, with our collaborators there, to raise funds to build a medical research institute and put it right in the center of the worst part of the epidemic on the globe. And then we got funding for a second institute there. And with those facilities, we were able to study large numbers of people who had just become infected and show that, in fact, everybody starts out making a killer T-cell response. It's just that in most individuals, those cells gradually become exhausted and dysfunctional, and then the disease progresses. So what more could we do? And this is where really the issue about scientific silos comes in. Our feeling was, there's a lot of knowledge in the world that's not being applied to this problem because scientific disciplines are so separated. And if we could break down those silos, maybe we could really see some progress. So this is really where serendipity comes in. We'd been working at a mission hospital in South Africa that had this very sophisticated medical record system, an electronic medical record system, an EMR. And I was asked to see the owner of it to tell him how important the EMR was for patient care and for research. So it turned out that person, Terry Ragon, lived here in Boston. So I arranged to meet him when I came back from Africa. And as I started to tell him about what we were doing, he said, gee, why are you building research institutes in Africa when you have Harvard and MIT right in your backyard? And I said, well, I think there are important insights that can be gained by studying the epidemic where it's at its worst. And said, you're welcome to come along and have a look for yourself. Never thinking that he would take me up on that. But 2 weeks later, found myself on an airplane on the way to South Africa with him. And when we got to South Africa, he saw the incredible extent of disease. And I'll just tell you one example. I just came back 3 days ago. Right now, among 15-year-old women where we're working, less than 1% are HIV infected. Among 25-year-old women, 50% or more are infected. So there's a raging epidemic still going on. He also saw our clinical facilities, the research facilities. He met with patients and with our collaborators. He saw his electronic medical record in action. And at the end of 3 days said, I don't see how anybody could see what I've just seen and not want to get involved, but I'm sure, or I assume you have all the funding you need from the government. How can I help? And that really kickstarted a discussion about the siloed nature of science and the fact that flexible funds to take innovative but risky ideas forward just didn't exist. We saw each other a couple times during the ensuing year, and each time he asked me about that idea of bringing disciplines together. And then one day he came to my office, and to my utter shock, he and his wife, Susan, gave us $100 million to establish the Ragon Institute of Mass General, MIT, and Harvard with the idea of bringing disciplines together, immunologists, computational biologists, physicists, engineers, et cetera. And with those new perspectives, we now took a new look at our situation of trying to understand HIV control. And for this, we applied statistical physics, social network theory to HIV structure. So in a network, a social network, there are certain individuals that serve as key hubs that keep the structure of the network together. And if those people become inactive, the network falls apart, or if they leave. So it turns out that viruses also act like networks, with key amino acids holding the network together and holding the structure of the virus together. What we found was that these HIV controllers were specifically targeting these critical hubs. And basically, in order to avoid the killer T cell responses, what the virus has to do is mutate those hubs. But that actually breaks down the network, cripples the virus, and that's how HIV control was being gained. So we had gone now from a situation where we had this new disease, it was a black box, we had no idea what was causing it, to an understanding that in certain circumstances, the body was able to successfully fight back. And what we had learned was that that these individuals that were successfully fighting back were doing so by having their killer T cells target these specific hubs, these nodes in the network. So in other words, what HIV controllers were doing was hitting HIV where it was most vulnerable. So now the question is, where do we go from here? And this is why I'm so excited. I think these findings are actually actionable. The challenge is to program the immune system in somebody with progressive disease and get it to function like the immune response in an HIV controller. So how do you program the immune response? Well, essentially, you try and teach the killer T cells to target these network hubs. And we think that can be done with a vaccine. And we have vaccines in development right now to try and do this. I'll be the first to admit that we don't know if this is going to work or not, but nature's successes give us a lot of reason to be optimistic. So I think that we're the future of human health, I think, is coming into better focus. And so much of it is because of the immune response. And we're seeing that already. And you've heard it in this conference. Vaccines that are protected from deaths from COVID, CAR T cells, checkpoint blockade, vaccines that induce T cells to cure cancers. We're really seeing it everywhere. And I think we'll see even more of that if we continue to work across disciplines and find out when the immune response is successful and when it fails, find out what makes it function and what makes it dysfunction. And if we learn from patients so that we can understand success when it happens, and then apply that, learning from patients to cure patients, and using that information to get the full potential out of the immune system by teaching it to do things that it's not already doing, I think that everyone in this room will benefit in the future from the really awesome power of the human immune system. So thank you very much.